So our first speaker is Tiffani Bright. She's M11, right? And she's currently a PhD student in Columbia University, and working under the guidance of Suzanne Bakken. She said she's almost done, and what you're going to see is sort of a quick preview of her thesis defense. So we are ahead of our committee even, right? So Tiffani, her talk is the title: A Computer-Based Alert for Reducing Inappropriate Antibiotic Prescribing. Tiffani.
Good morning. So I'm going to discuss an informatics approach to addressing the resistance problem. We're going to begin with an introduction into the problem of antimicrobial resistance, and we will move throughout the talk from there. So first of all, antimicrobial resistance is a significant global health issue. Research and development in antimicrobials has declined significantly since 1983. Therefore, one of the most effective and immediate solutions to address the antimicrobial resistance problem is to look at the role of inappropriate antibiotic prescribing. And this, here we go. This is just a diagram showing some of the contributing factors to antimicrobial resistance, because it's not only about prescribing. You've got consumer knowledge, natural evolution, use of antibiotics in agriculture and stuff. So just a little overview, although we're focusing on prescribing practices. And I mentioned it's a significant problem, and these are some key statistics that are pretty much everywhere when people talk about resistance. So nearly 2 million patients acquire an infection in the hospital yearly, and about 99,000 of those die. It's estimated that at least 70% of the nosocomial infections, or hospital-acquired ones, are caused by one antibiotic-resistant organism. It's also estimated that 1/3 of the given antibiotics are in fact unnecessary. And what this adds up to are increases in morbidity, mortality, and treatment costs. So with this in mind, our lab decided to think about what could we do to use computers to help address the problem. And our study goal is to create, implement, evaluate an antibiotic microorganism mismatch alert to notify the clinician when a patient's organism is resistant to the ordered drug. So what you're looking at, it's called a mismatch because you're looking at the bug and the drug. And if you order an antibiotic and the patient's resistant to it, we want to notify you. This is kind of showing you our study design. It's nice to see a picture of what you're talking about. So we've got this mismatch alert, and it's got a knowledge base. And our knowledge base is based on this ontology, which I'm going to talk about in a few slides later, but just so you kind of see where things fit in. And we're going to do some brief background into the problem of resistance as well as how we're addressing it. Antibiotic misuse involves two main players. You've got patients and you've got clinicians. And so patients will often demand antibiotics when they're not clinically indicated for a bad cold, or fail to take the full dose, and this creates suboptimal therapy. So what happens is the weaker organisms die, the resistant ones survive and thrive, as well as self-medicate, so take leftover antibiotics or someone else's. And then from clinicians, you have the pressure from patients. You also have a lack of time to educate about when antibiotics are appropriate, and malpractice concerns. So if I don't give an antibiotic and something gets worse, am I going to be responsible? Since we're focused on prescribing practices, we're really targeting clinicians. And that made us think about, well, exactly why is this happening? So we did a literature review, conducted some observations with the infectious disease team, as well as a couple of interviews. And we classified the reasons into two categories. First, you've got a lack of education pertaining to infectious diseases. So what's the significance of the isolated organism? What are the antibiotic classes? What's the recommended one for this particular bug? And then there's the lack of available information at the time of a decision. So unique culture results, medication allergies, as well as risk factors for resistance when you want to make the best antibiotic decision. And so we've got these reasons, and we decided to use clinical decision support to really be a solution to the problem. I'm not sure if everyone's familiar with it, so broadly, it's clinical decision support is it's defined as a computer-based system that helps clinicians make clinical decisions to enhance patient care. And what the research shows us is that you can use clinical decision support to modify prescribing behavior when it comes to antibiotic prescribing. So these systems can help clinicians select the appropriate antibiotic therapy, support decisions with evidence-based medicine and guidelines from the CDC and such, as well as preventing medication errors. So just to draw home the point that the antibiotic microorganism mismatch alert that we're designing is an example of a clinical decision support system. To build our alert, we're using ontologies, and they're a great method to represent and share domain knowledge through modeling the concepts and relationships within a domain. And the advantages of ontologies is it provides you a common structure of information, and we can share this from different applications. You can reuse domain knowledge that is already validated in the community, as well as integrate other ontologies and other features in it. So we're going to use an ontology to support our alert to really modify prescribing behavior. Now, for our aims, we identified three. First, we identified the functional specifications for the antibiotic microorganism mismatch alert. So we said, well, we went to the clinicians and said, what do you need in an alert to help you with your prescribing? Two is to develop and validate the antimicrobial microorganism ontology. So this is to support our alert. So now that we know what you need, it's like we went and built it. And three is to evaluate the effectiveness of the alert, because at the end of the day, we want to know, now that we've built the system, does it help the clinician? And we're going to focus on specific aim 2, which is how do we develop this ontology? When you talk about ontology development, there's 6 main steps. First of all, you figure out what's your domain. And for us, it was antimicrobial as well as microorganism. Then you try to reuse existing ontologies and standards. So we're using the infectious disease ontology. It's an open source ontology that's coming out of the National Center of Biotechnology, or NCBI. We're using that, and we're also using SNOMED-CT, which is a comprehensive clinical terminology standard. And it's not only a US standard, but it's an international standard. And the main step of our ontology development is to really focuses on developing these classes which represent your individuals in a domain. And what we did was, so this is from the original IDEO ontology, and it reads that antibiotic is an antimicrobial. And we then expanded that using SNOMED-CT to populate the subclasses. So then in our case, you get something like azithromycin is a macrolide, macrolide is an antibiotic, and antibiotic is an antimicrobial. So now this is this common structure of information that you have that we can share across applications. That's the first benefit of the ontology. The second is you represent these relationships between these classes. So you define properties such as antibiotic treats bacterium. That's really simple for us, but you need to state it for a computer. And then once you do your properties, you talk about individual instances, and this is where you use clinical knowledge to really support your alert. And an example would be that penicillin G treats Streptococcus pneumoniae for penicillin susceptible, and yet we would use vancomycin if it's penicillin resistant. So this is the type of knowledge that you represent in an ontology. And the final step is you validate it. We're using Protege Owl, which is an ontology editor. It's open source. It's from Stanford. And it includes these things called reasoners. And so you want to go through and make sure everything is defined, and we could talk about it, but that's what you use to really validate it. And it's a very iterative process. You kind of go back and forth to really define your classes. But we have some preliminary results. And you can measure the breadth and depth of an ontology using things, ontology metrics such as the number of classes, properties, and restrictions. So we originally started with 184 classes, and then we expanded to 434, as well as added a number of properties and restrictions. And a couple of examples, so macrolide is an example of a class. It's an antibiotic class. And a property, again, would be treats. Then you would see something like this restriction, and then to translate in English, it says that if something is a member of the macrolide class, it has some mechanism of action of inhibit protein synthesis, because you've got 5 broad categories of mechanisms of actions of drugs. And so this would exclude things like penicillin G, because penicillin G works on the cell wall. So this is how you would define members that belong to the macrolide class, such as azithromycin. And I do have an example of protege al. So this is our developing ontology. It's not complete, but our hierarchy that I showed you a little bit earlier with that ISA relationships. And in here you provide some of the properties as well as the restrictions. So if somebody is a member of the azithromycin class, they have some of these things, some of these features, because one drug treats multiple diseases, so you have to build a system for that. And to just wrap it up, what we've discovered is that clinical decision support is an effective method to address antimicrobial resistance, and ontologies are essential about that, essential component for knowledge reuse as well as representation. So we're finding that an ontology can support our alert and modify prescribing behavior. And again, the principles of reuse and sharing knowledge base. So not only can we use this for this one antibiotic alert, but we can also go ahead and create another alert, such as de-escalation, so notifying clinicians that after 48 hours, please reduce from a broad antibiotic to a narrow spectrum. So you can use it for multiple purposes, and our next steps are to complete the ontology and then validate it and evaluate the effectiveness with the clinician. So I'd like to thank my committee members and my funding source. Questions? That's a great question. Well, that's one of, and when computer scientists talk about ontologies, that usually ranks in their top feature, is that maintenance is key. So if you have a knowledge base and it says for this condition, we recommend this drug, but that's outdated, then you're putting the patient at risk. So with an ontology and in Protege Al, it's very simple to go in, and you would simply just, it helps with a maintenance task. It's actually less intensive when it comes to maintenance. So we would go into our ontology editor and take that restriction that you saw and say, well, in this case, we're going to change it that if something is a member of this, you now do X. And so you just modify the rule. So it's pretty intuitive. And so we're actually measuring that now with our domain expert, so someone who actually is in the hospital and creates the rules. We have a study set up, it's a cognitive walkthrough, and they kind of go through a number of steps to update the knowledge base, and we're comparing to see if this really is less intensive as we've been told it would be.
Could I ask a follow-up on that one? Is the maintenance at the clinic level, or is it in a more...
It's at the knowledge, it's for the knowledge engineer. So the way it works at our facility is that the clinician doesn't have anything about the background, so they wouldn't interact with the system. It would really help the knowledge engineers, and they would be able to make, well, it's 2 parts. So first of all, it's the knowledge engineer who would update it, and then we have a web interface. So this is put into the clinical environment, and they wouldn't see, the clinician wouldn't see what's going on in the background, but it would help the knowledge engineer.
I will assume that this knowledge-based method, it will assume that you know the medical history of the patient.
So you would. So the way you can implement clinical systems in a various number of ways, but the most effective is to actually implement this tool into a computer, into a CPOE, which is a computer physician order entry system, or electronic health record, and they would have the history of the patient, because something like medication errors, we have to account for it in our ontology, such as penicillin allergies. So we have a class that talks about allergies. So in our rule base, we have to say if patient has allergy, then don't order this. So we do have to take into account medication allergies as well as risk factors. That's a really key. So if you can build a system that can say, based on the patient's prior antibiotic use based on the fact that they've had invasive devices for the last 7 days, et cetera, they might be at higher risk. That's something that we're building in because that would be really helpful to a clinician.
How do you address, nowadays people may receive health care from various entities. How do you integrate all of that knowledge?
We haven't figured out how to do that. That's something that's out of the scope of our ontology, our scope right here, but I think that's a very tough question. I think that everyone is struggling with how do you integrate knowledge because, like you said, you can have multiple providers and get prescriptions from each, and there's bound to be a medication error that could occur, but I think that's a larger issue that requires standards that everyone's trying to address.
I think that would be focus.
Okay, thank you.